Hello, everyone. And today I will present about the subtask 3 in PVPS task 16, which is on solar forecasting. And a lot of people use forecasting for solar because we want to know what our solar power plants will produce in the future. And the main the main product used, in at least in my experience, is numerical weather prediction, which is something that is run on a global scale by, for example, the European Center for Medium Range Forecasting, and also on regional scales by a lot of national meteorological institutes like DMI, and they run a forecast model that is on a um, on a higher resolution, just a slight smaller scale, but they even use the global numerical weather prediction model as sort of an initial input and boundary for the more local model. And this is the one by DMI that Irene will also mention. Um, it's something we all use every single day on our mobile phones, for example, where solar radiation is also a product of that. And one of the biggest activities in task 16 right now is a new study. I don't see this slide on the computer. He gone. He went. Okay, I'm just going to look up here and look at this with you instead of looking at the laptop. It's a new study that is kind of new in the sense that we do it again. But it was actually done quite a few years ago. But this is an update on a worldwide numerical weather prediction model benchmark, where what is benchmark is the global horizontal irradiance outputs. And there will be both global models used in this, and there will be regional numerical weather prediction model used, and as the models that are benchmarked, and they will be benchmark tested against ground stations, where, for example, both the station that Adam just showed you a lot of pictures of and the station that we have here at Risø will provide the ground measurements as the ground truth. And this requires, for example, Class A instruments. It's of course also requires quality control of the ground measurements and that the stations pass quality control. And it is expected to be finished by March 2027. It's a bit of in the future, but I think this will be a very important work coming out of the task because so many people use numerical weather prediction models. And then activity 3.4 is on forecasting based on cloud images. And cloud images can be captured either with the what is on the left here in the image, an all sky imager. So this is any camera that captures a 180-degree field of view image of the hemisphere mounted horizontally, or it's cloud images based on channels of cameras on a satellite. And what is typically used here in Europe is Meteosat second generation or the Meteosat third generation. And we really care about clouds a lot because they are what causes the non-deterministic part of variation in the solar resource. If we just had no clouds at all, it would be fairly easy to know in the future what solar resource would be. But clouds are an issue here. And there is a report on comparison satellite and all sky imagery based forecasting and on hybrid, like blended approaches, which is coming out around April, but I think it's more likely summer 2026. We discussed that recently in the group. And then a new project is starting up, benchmarking review paper to summarize state-of-the-art forecasting methods, where it will be both statistical methods, machine learning based methods, blended of the techniques. And this review, the intention is that it can be a reference document that people can use for a long time to see, okay, at this point in time, what was the state of the art? And it should be for both researchers and industry. And the task's main function is kind of to figure out, in this case, what is the gap and what do we need to intensify research on to improve these techniques. And then I want to talk about some of the things that the people participating in the task has presented recently. One is using cloud images for optimization of PV tracking. This is something Adam also touched on. But here you can actually use the images as a way of figuring out what the distribution of radiance across the hemisphere is. And this is some work done at TotalEnergies where they took cloud images and they also have measurements of radiance from all points of the cloud. They kind of scan it. Um, and then they calibrate the camera. And I think, yeah, so if you overlay it, you can kind of see the radiance in watt per square meter per steradian across the entire hemisphere. And if you then calculate what would the panel see, depending on its tilt, then you can find the optimal. And it's actually they actually found out that it was quite different compared to the standard method used today, which is applying the Perez transposition model, where you can see the darkest blue represents the new method based on cameras, and the lighter blue represents the current best practices or current normal practices, where you can see on a clear sky there is a slight difference both in the optimal tilt, which is on the x-axis, and the PV yield of the module at that tilt on the y-axis. And on a cloudy day, there's actually a significant difference where the research showed that not being horizontal during cloudy periods can sometimes yield more energy because the radiant distribution across the hemisphere is not 100% uniform, even though it would look like that on a day like today. Other research also from partly from TotalEnergies, but also from Mine Paris, is using a combination of satellite images from above, looking at clouds, and cloud cameras on the ground looking at clouds from the bottom to kind of triangulate in the way that the visual shows here exactly where in the atmosphere the clouds are. And this is super important because when you have a picture of clouds from the bottom, if they're very close to the ground or very far from the ground, you can't really tell from a single picture because it's like if you close one eye, it's kind of hard to judge distance. It's the same concept. So this kind of gives us two eyes in a sense, and you can figure out where in the hemisphere the clouds are, and then where their shadows are cast on the ground. And this is a way of improving the cloud height estimations. And the DLR have been presenting some work on using a combination of satellite images and rain radars, weather radars for doing a bit of the same, identifying cloud locations. And they did this across all of Germany, where they took the data from all the the rain radars on the left image here and satellite down there, and they combined it into kind of a cloudiness map and used that to forecast with. And then some of the work that we do here at Risø in the research group Solar Photovoltaic Systems. We have a PV system about 440 kilowatt peak built in the north end of the campus together with European Energy Commission, I think January 2017, 18, yeah, which we use for research purposes. And we have also installed cloud cameras. There are four cameras in total, one at the pier, which is, some of you might even be able to spot it, the pier down through the windows there, one at the wind department on a building over there, and one right next to the farm. They're about 1 kilometer apart, which is somewhat optimal for the cloud conditions we typically find here in Denmark. And we plan to use this for forecasting very short term of irradiance. So here I show how you can have a map of where on the ground there is shadow and where there is no shadow based on images. So this is kind of the product that it gives you. And you can use this together with a digital model of a PV system to estimate the power output of the PV system. And this is some of the research we will be doing, is estimating when ramps will occur and can we properly predict those. Something like 25% of the PV system capacity per minute is a ramp limit that you sign when you have a grid connection here in Denmark. And we want to see, can we actually properly estimate that in order so that the operator can act on it preemptively. And we also will be researching cloud height estimation. So we recently installed a ceilometer, the somewhat tall instrument shown there in the meteorological station here. And we will use that as a ground truth when testing different methods for estimating cloud heights. Here I visualize kind of how the cloud height is important because if the clouds are really high in the atmosphere, your vision is very broad. But if it's a low cloud cover, you don't see very far with the camera. So it is one of the biggest issues for cloud camera-based forecasting is the cloud height right now. And some of the things that we're looking for information or collaboration on is how our TSO Energinet's balancing process can integrate local forecasts or satellite forecasts as well. How traders, balance responsible parties can incorporate satellite and cloud camera fusion in decision systems. I know that they are already doing that, at least the more active or on the forefront of it, of the traders? And how can PV operators use this to unlock some value without major changes in how they operate their systems? Thank you.